So number one, at low frequencies, Ci is infinity, and Rb theta, and the medium frequencies and high frequencies, Ci is shorted, so that we have Rb only. So we start out the omega, and then this one goes down so that we have Rb plus theta plus Rl as the resistance here, and the minus x and R plot. And then we have a Warburg, so that we have a 45 degrees, and the A value is proportional to the diffusion coefficient, but it maintains 45 degrees. And here at this end, we are going to have resistance corresponding to Rb plus theta. And then we are going to have a semicircle, and then here the value is going to be Rb, and you're going to have another semicircle to the end, 0. And so this is, as we move to the omega, something like this. Okay? And this value, omega CIRB is equal to 1. And here, this value, omega CGRB is equal to 1. So this is the total AC impedance spectrum for the Randall circuits. Randall circuit means the Rb and double layer capacitance and charge transfer resistance and Warburg impedance is connected to the geometric capacitance Cg. Okay, and then that is the representation of the system, that M, Mx, Mxy, mixed conductor. That is the most typical cases for the battery system, right? So with the proper selection of the frequencies in the measurements, then we can have this whole figure, and then we can determine each factors there. But in reality, the values, depending on the values, each values some of the semicircles should be overlapped. Like if the first thing is this small and the second thing is this large, then the AC impedance spectrum that you can see is just this. Okay? And then if the this is the plot that you're supposed to have, but if the diffusion coefficient is very slow, then this moves toward this direction, something like this, so that you end up with some plot which is going to be look like this. So it's not that distinctive. It's not that clear. But it just depends on the values that you have, the RB and theta and the CI and CG, things like that. So you have to be careful about this. And even there's a 45 degrees, sometimes it is not going to show you exactly 45 degrees, because some other element is related with that, then it's not going to be 45 degree at all. Like a temperature, for example, and then side reactions that is involved. If this side reaction is involved, then this 45 degree is going to be changed. And this straight line also is going to be changed as well. Okay? It's going to be tilted like this. It's going to show the different slope. If you have if your system is deviated from the ideal values. Okay, that is about the AC spectrums, and as you have seen, it has very powerful. It is a very powerful technique, and in the developing a new cathode materials. Okay, of course, the development of anode materials is important. We cannot neglect that, but the capacitance that your electrochemical system can show is very much dependent on the cathode materials. So development of a cathode materials is very important. And also the ionic electrolyte is also important, especially if you want to make all solid state batteries. For example, if you want to make a tiny batteries, which might be used for the medical applications, injection with the needles into your blood to measure the temperature, whatever, then you can make a micron size batteries, and then you can inject that battery into your blood to find the temperature at exact locations. Okay, that is possible. And then for that, the first thing that we have to do is make all solid state batteries. And the cathode and anode solid state materials, it's usually solid state materials, solid and solids. But the electrolyte is always, it's a liquid. Well, recently people working on the polymers and Joule-Gel, things like that. But the reason why most of the batteries uses the liquid electrolyte is that the ionic conductivity. And the electrolyte, the ionic conductivity should be very fast. And it is very difficult to realize the high ionic conductivity in the solid. So up to now, most of the battery system uses the liquid electrolyte, so that the packaging becomes an important problem. So it prevents us from having very tiny micron size batteries. So anode, electrolyte, cathode, everything is important. But when you're talking about the new batteries, high capacity batteries, most of the researchers are focused on this cathode material. Okay? And it's wide open because the the battery systems that we are using now, everything becomes mobile. Robots and computers and handphones and everything. So the energy is very important, becomes very important these days. But as far as the battery is concerned, the basic concept never changed. And in my opinion, the study on the batteries are not developed fast as the needs enlarge this area. Okay, so I hope more researchers will do the research to find a new energy storage materials in the batteries. Okay, on Wednesday we are going to talk about the fast ionic conductions. Fast ionic conduction is very important in the development of the electrolyte, solid electrolyte especially. The liquid, we don't have to talk about the mobility of the ions, conductivity of the ions, because it has a high enough mobility. It's in the liquid. But in a solid, we need the super ionic conductors. So the rest of the lecture is focused on the fast ionic conductors, focused on the development of a solid electrolyte, the basic kinetic nature and things like that. Okay, I'll see you on Wednesday then.